Hello, my name is Fariba Mostajeran from University of Hamburg, and I would like to present our paper about augmented reality for older adults, exploring acceptability of virtual coaches for home-based balance training in an aging population. Falls are a major concern among older adults, as approximately 1 out of 3 people above 65 and almost half of the older adults above 80 years of age fall every year. The consequent injuries can vary from a scratch to hip fractures, and the hospital stays due to falls can be long and even last for the rest of the patient's life. Balance training at home has been shown to be effective in reducing risks of falling. They are recommended to be prescribed individually and monitored by a trained professional. However, the prevalence of aging population at risk of falling overwhelms the availability of experts to provide this treatment. In this work, we followed a human-centered design approach and iteratively developed an augmented reality-based balance and cognitive training solution for older adults. Our solution offers a virtual coach that presents instructions, demonstrates correct performance of the balance exercises, and gives feedback to the users about their performance. A holographic representation of a virtual coach displayed via an augmented reality head-mounted display has several advantages over flat visualizations on monitors. For instance, it allows the users to quickly identify 3D poses in the space and enables them to look at the virtual coach from any angle. It is also possible to stand next to the virtual coach and see the instructions from the same perspective, which reduces the cognitive load of mental rotation. Also, an optical see-through augmented reality head-mounted display is beneficial for our application scenario compared to fully immersive virtual reality head-mounted displays. This is due to the reason that augmented reality head-mounted displays allow the users to see the real environment with its own physical objects and obstacles. Therefore, in case the older user feels that a fall is about to happen, nearby physical objects, such as a firm chair or wall, are in sight and can be grabbed to prevent the fall from happening. Since we had a requirement to use a light, affordable, and cable-less AR head-mounted display, we used a smartphone capable of displaying AR, in this case, a Pixel 3 XL phone, which was integrated in the lightweight Ocular AR headset. To detect the correct performance of the exercises, we used several wearable sensors, including pressure insoles, 2 IMUs, and a depth camera. In addition, we used a heart rate sensor to be worn on the chest and a fitness wristband. We had also augmented reality exercise games. In this example, users should walk across the room towards the deer. Furthermore, studies have shown that falls are associated with lower cognitive performance. Therefore, we offered several cognitive games. In this example, an AR memory game is shown in which the user should remember the sequence of the cards and recall it after it has been shuffled. We had also an auditory training tool for training speech and noise detection and auditory memory. In this example, the speech and noise detection task is presented. Its user interface shows animal pictures and colored numbers. Following an audio instruction, such as show the dog where the blue 5 is, the user should click on the correct colored number. Example, the blue 5 button here. Additionally, the instructions contain different background noises, for example, cafeteria type noise. The training plan is prescribed and monitored by physiotherapists using Dashboard, which is a web-based application in our project. And users themselves can monitor their physical and cognitive performances using a smartphone app. This app allows the users to see their performance by means of charts, pictograms, and badges, for example, when the goals are achieved. Moreover, the app contains a calendar which shows the training program as well as a social networking feature to communicate with other users of the system. The data collected from the sensors are fused and analyzed on the edge computer, which is a computer at user's home, and provides real-time feedback to the user articulated by the virtual coach. The results are then sent to the cloud to be monitored by the therapist. Based on the user's performance, the therapist can adopt the exercise program. In order to provide a system with optimal usability, the human-centered design approach was followed in this work. Through an iterative development cycle, the requirements were analyzed, different versions of the prototypes were implemented, and evaluated by all the adults. After each iteration, new insights were evolved, which led to re-prototyping of the concepts. To evaluate different iterations of our implementations, we performed multiple focus groups and semi-structured interviews with a total of 76 older adults in 3 countries across Europe, in England, Germany, and Greece. In this work, we pursued the answers to the following research questions. How acceptable and usable is our AR-based balance and cognitive training solution for older adults? And how is the virtual coach perceived? In the first iteration, 5 older adults in London with an average age of 74.8 years participated in our first focus group. All 5 participants used the then available system. The average system usability scale, or SUS score, was calculated as 72.5, which is considered to be above average. While using the system, the older adults saw 5 profiles of the virtual coach. They are from left to right, the commonly used representations in AAA games, here the realistic male and female avatars, and then male and female cartoon avatars that are commonly used representations in commercial EXA games. And the last one was a polygonal 3D reconstruction of a real human that is commonly used in high-end telepresence applications. As a result, 60% of the participants preferred the realistic male virtual coach. So in the second iteration, we continued with this avatar only. Our second focus group, again in London, was intended to verify if the previous findings of the first focus group were representative. Here, the participants did not use the system and instead saw a live demonstration of the system. 47 older adults with an average age of 73.61 took part in this focus group. Our participants were positive and confident about using all modules. And assistance to use the system was not foreseen as requirement unless it is a technical assistance at the start. In the second iteration, the requirements and user preferences gathered from the first 2 focus groups were used to further iterate the prototypes. In order to address the accessibility of our solution for the older adults in different locations, the third focus group was held in Freiburg in Germany and the fourth in Athens in Greece. For the purpose of these focus groups, all prototypes and questionnaires were prepared in both German and Greek languages. This video shows an older adult in Germany wearing the head-mounted display and performing an EXA game. The results of the last 2 focus groups, with a total of 24 participants, showed that the virtual coach was perceived as an alive, calm, intelligent, and friendly human. The results of the user experience questionnaire suggested that the participants found our solution attractive, novel, and stimulating. The overall workload during testing can be also considered as low to medium. However, the usability of the entire AR solution showed a significant negative correlation with participants' age, meaning that the use of our system for participants in their 60s was significantly easier than those over 80 years of age. Indeed, we observed that some 80-plus participants did neither have internet at home nor mobile phones or computers. And as a result, they had difficulty interacting via the smartphone's touchscreen. In sum, in this work, we pursued the answers to the following research questions. First, how acceptable and usable is our AR-based balance and cognitive training solution for all the adults? Our evaluations showed that it depends on their age, as the usability for 65 to 79 years old participants was good to okay, and for 80 plus was the worst imaginable. Our second question was, how is the virtual coach perceived? And the answer is that the virtual coach appeared socially present in the physical room like an alive and intelligent human. In the end, we would like to express our special thanks to all our participants and our project partners, as well as the European Union, for supporting us. Thank you for your attention, and for more information, please refer to our paper.